Here are problems 5, 6, and 7 from the equilibrium review. For problem number 5, force of gravity pulls down. There's one tension up. Here's another tension up. There's no acceleration because the object is just hanging, so my up stuff is going to equal my down stuff. Here we go. 2 upward tensions equals force of gravity. T plus T is 2T equals force of gravity. So if I'm solving for tension, I just have to divide by 2. And the mass times 9.8 divided by 2 gets me 39.2 newtons for each tension pulling up on this thing. Number 6, let's just take a look at the 5 kilogram mass here. Don't even worry about anything above it. This rope right here does not know that it's hanging from another weight. It could be hanging from the ceiling. It doesn't know and it does not care. So this tension here has to hold up all of this weight, which is why for the 5 kilogram mass, the tension up equals the weight of just that 5 kilogram block. It does not matter what's happening above it. So the tension here, T1 up, equals the 5 kilogram mass's weight, which is 5 times 9.8, which is 49 newtons. For the 8 kilogram block, when we set up our equation here, this one is being pulled up by tension 2. The 8 kilogram block has its own weight, which is why it has this little force of gravity 2. And also the 5 kilogram block is hanging from it. So the weight of the 5 kilogram block is hanging from it via this rope, which is T1. So my upward force, T2, has to equal both the downward forces, how much the 8 kilogram block weighs, plus the 5 kilogram block hanging from it, which is represented here by T1. So the upward tension of T2 has to equal the weight of the 8 kilogram block and basically the weight of the 5 kilogram block, which is 49 newtons, plus 8 times 9.8, for a total of 127.4 newtons for this top rope. For number 7, this 50 kilogram object is being pulled at a constant speed by pulling it at 200 newtons at this angle here, 30 degrees with the horizontal. T in the X is to the left, Ty is up. First thing that we want to do after we've drawn our picture is solve for our tension in the X and tension in the Y. So how much am I pulling this left? How much am I pulling this up? Because tension in the X is the adjacent side, I'm going to use cosine of my angle 30 degrees times how much I'm pulling it, which is 200 newtons. So I know I'm pulling it to the left with a force of 173.2 newtons. Tension in the Y is going upward. That's the opposite side. I'm going to solve that using sine of 30 times the amount that I'm pulling, which is 200 newtons, telling me that I'm pulling it upward 100 newtons. If I redraw my forces, I have normal up, gravity down, and don't forget this tension in the Y is up, which is why we have 2 upward, Ty and normal force, and force of gravity is down. To the left is tension X, to the right is friction, so tension X left, to the right is friction. So if I take a look at my right and left, there's no acceleration because it's moving at a constant velocity. So my right stuff equals my left stuff. So my right force is force of friction. T in the X is to the left, and I know that's 173.2. So my force of friction is 173.2. Up and down, my up stuff is going to equal my down stuff because, again, there's no acceleration. My up arrows here are Ty and the normal force. So Ty and the normal force are added together. Force of gravity is down, so my 2 upward arrows equal my down arrow. Normal is going to then equal force of gravity minus Ty once I subtract Ty over to the right side. And now I can plug in for some of my numbers. I know force of gravity is mass times 9.8, so that's 50 times 9.8. Ty we already solved for earlier in the problem is 100. So 50 times 9.8 is 490 minus 100 gives me a normal force of 390 newtons.